The next presentation will be Aliona Nicolenco. Now she is from Barcelona. Functional properties of iron gallium alloys prepared by electrodeposition. So let's start.
Thank you, Henrikas, for the introduction. First of all, I would like to say that I'm very happy to join this meeting today and see you once again, even though it's a virtual meeting. But yes, as Henrikas mentioned, today I'd like to show you some recent results that we obtained in our group, working on functional properties of iron gallium alloys prepared by electrodeposition. So this work was done in collaboration between several groups. The group of Institute of Applied Physics of Moldova, Vilnius University, EPT company in Lithuania, and also Autonomous University of Barcelona, where I'm working now. So here's the outline of my talk. I would like to start with some introduction, talking about the properties of iron gallium alloys in general. Then I'd like to focus on the electrodeposition process of iron gallium alloys that we used in this work, and how we introduced different porosity levels to the films. And then I will be talking about the mechanical properties and magnetic properties of these obtained materials. Then in the final part of my presentation, I will demonstrate to you a proof of principle of magnetoelectric actuation that we could perform using this kind of electrodeposited films. So why iron gallium films? In fact, the main property that we're looking for in these alloys is their high magnetostriction. So what is magnetostriction? Is a property of magnetic material to expand or contract under the action of external magnetic field that actually occurs due to the reorientation of magnetic domains when the external field is applied. So this property, in fact, allows a conversion between electromagnetic energy and mechanical energy or strain, and that's why these films, iron gallium alloys, are widely utilized for the fabrication of various sensors and actuators. We also know that the magnetostriction properties strongly depend on the composition. So, for example, here we have the change in magnetostriction coefficient as a function of gallium content. So there are like two maxima that corresponds to 20% of gallium or 30% of gallium. So these are the two compositions that we will be trying to achieve in this work. So among the other interesting advantages properties of these films are their mechanical properties, such as ductility, for example, biocompatibility and biodegradability. In terms of magnetic properties, they have soft magnetic behavior and high saturation magnetization. And well, last but not least, they are easy in fabrication, especially when you compare them to some other magnetostrictive materials that are quite difficult to fabricate. So due to this number of properties, of interesting properties, iron gallium alloys recently became interesting for the fabrication of so-called magnetoelectric composites. So in these composites, there are usually two phases. So one phase is magnetostrictive phase. This is the phase that can generate strain under the action of magnetic field, and in our case, this could be our iron gallium fields. And then the second phase is a piezoelectric material. Piezoelectrics have a property to generate charges, to change polarization state when they are strained. So when these two phases are coupled together, we can produce a composite material where the external magnetic field will generate strain in the magnetostrictive part. This strain will be transformed to the piezoelectric part here at the interface, and this material will generate charges. So like this, we can modulate the electric polarization of a composite material by applying external magnetic field. So these kind of composite materials have found applications recently in these three different areas. One of them is energy harvesting. So imagine that there is a wire and there is a current flowing through this wire. So this current will create some magnetic field all around, and imagine that we coat this wire with this kind of magnetoelectric composite. So the magnetic field will generate strain in the magnetostrictive part that will be transferred to the piezoelectric part, generate charges, and these charges can be collected. So like this, the part of the energy can be harvested. Another application is for water remediation. So for example, here we have a core shell nanoparticle. So then when the magnetic field is applied here, again, we will generate some charges on the piezoelectric counterpart of this particle. So this charge will be enough to initiate some electrochemical reactions at the surface and produce some active species that may be capable to destroy some organic pollutants like dyes or even some drugs. And the other area of application is wireless self-stimulation. So in this case, again, we can electrically stimulate cells by applying external magnetic field, and actually this technology represents nowadays a non-invasive way for self-stimulations, because we can do it externally with magnetic field without the need of implanting electrodes. So as you can see, these composite materials may have different architecture, different shapes. So this can be like a layer or core shell nanoparticles, or I don't know, hybrid nanowires. So there are many architectures that can be exploited. And recently, nanoporous materials also become attractive for the magnetoelectric actuation due to several reasons. One of them is their large surface to volume ratio. That is extremely important for some magnetoelectric applications where we need to accumulate large amount of charge at the surface, or when the material is immersed in the liquid electrolyte and then the porosity facilitates the formation of the double electric layer all over the surface and inside the pores. Then the nanopores can also accommodate various gas materials. This is another example. Here we have a mesoporous bismuth ferrite matrix that is filled with nickel by electrodeposition. Nickel, by the way, is also a magnetostrictive material, even though its magnetostriction is much less than for iron gallium. But in this way, another kind of magnetoelectric composite can be prepared. Or in this case, for example, we have a polymer, a piezoelectric polymer, that is filled with magnetostrictive cobalt ferrite nanoparticles. And in this work, they targeted again for some composite materials where the magnetoelectric effect can be induced locally with the external magnetic field. Then, interestingly, the nanoporosity can also bring some mechanical flexibility to the films. So, for example, in the continuous films grown on the rigid substrate, there is a so-called clamping effect. So the film is strongly bonded to the rigid support, and even when the magnetic field is applied, there is no way for the material to deform. However, if the material is made porous, then the bottom of the ligaments will be still clamped to the substrate, but the top, the top side of the pillars, maybe of the ligaments, may be still expanding or contracting due to the absence of lateral constraints. So in this work, we were preparing iron gallium alloys by electrodeposition, and we employed a standard 3-electrode cell. However, the working electrode in one case was just a flat, not patterned silicon substrate metallized with gold for conductivity, and the films were directly grown on the substrate. However, in the other case, to induce high degree of porosity to the films, first, at the initial step, we deposited some polystyrene spheres using electrophoretic deposition on the on this silicon gold chips, and then this patterned substrate was used as a working electrode. So during electrodeposition, the film was growing everywhere between the spheres. And after electrodeposition, we could remove the spheres in the organic solvent, in tetrahydrofuran. That afterwards, after the spheres are removed, so we are left with this kind of porous structure in iron gallium films. We also used We also prepared an iron gallium sample, reference sample, by sputtering. These are physical method, deposition method. So we will consider this reference sample to be fully dense and we used it for mechanical and for magnetic measurements as a reference sample. So this graph here on the left-hand side shows you the change in alloy composition as a function of electrodeposition parameters such as deposition potential and the pH of solution. So we can observe that at a given potential, there is more gallium incorporated in the film when the pH is increased. To understand this behavior a little bit, we performed some species distribution calculation that is shown here on the right side. And indeed, we can observe that when the pH is increasing, there is an increased concentration of gallium hydroxide species, like this one here and this one here. And we know from literature that these species are quite electrochemically active, and they participate in the electroreduction mechanism. Also, we can see that in this region, there is a decrease in the sum concentration of iron hydroxyl complex and iron complex with the citrate. Citric acid here was used as a complex reagent. So all this together indeed supports the idea that probably gallium is will be preferentially incorporated at the higher pH. So interestingly, that we can observe from this graph also is that when we perform electrodeposition on the templated substrate, so the substrate with the polystyrene spheres, the films have a higher gallium content as compared to the non-templated substrate. So this again can be due to the alkalinization of the near electrode region that shifts slightly the equilibrium towards the formation of the gallium hydroxide species. And also we can suppose that probably the diffusion of iron citrate complexes may be hindered within the narrow channels of the porous of the colloidal template. So here is the morphology of the obtained films as a function of their composition. So as you can see, it indeed changes significantly with the increased gallium content. But what is common for all of these films is the presence of some porosity degree, actually. So that is why we call these non-templated films nanoporous, because there are some nanoporosity in between the grains. And we believe that this porosity originates from the highly distorted columnar growth characteristic for these films. For example, this is the fracture surface of iron gallium film with 20 atomic percent of gallium. So we can indeed see some spaces between the kind of columnar grains here. And in this image, we can see the top surface of the colloidal templated iron gallium film. So we can observe this very large pores. Actually, their size corresponds to the diameter of the polystyrene spheres that we use as a template, and it is about 400 nanometers. The mechanical properties of electrodeposited iron gallium films were studied by nanoindentation technique. So in this slide, we summarized the most important results of this investigation. So in this graph, we have the corresponding low displacement curves recorded on the sputtered reference sample that also had 20 atomic percent of gallium in composition. Again, we focus on 20 and 33% because this, according to the literature, corresponds to magnetostriction maximum. So the reference sample, then the non-templated iron gallium film grown on the silicon gold flat surface, and the two templated films that were produced using colloidal templates. So from these low displacement curves, applying the method of Oliver and Farr, we could extract the values for elastic modulus and the hardness and they're plotted here. These are just the extracted numbers. So we can observe that in both cases, the highest values are obtained for the reference sputtered and fully dense iron-gallium film. While for the same composition, for example, for 20 atomic percent, both of these parameters, elastic modulus and hardness, decrease with the increase in porosity, and we also notice a decrease in both of these parameters with the increased gallium content. Even though another parameter that we could obtain from the low displacement curves is so-called plasticity index, that is shown here in this column. So this parameter actually shows the ability of material to absorb plastic deformations. So even though the hardness and elastic modulus decrease, the plasticity index is increased for the nanoporous and highly porous samples. From the nano-indentation data, we could also extract the porosity degree according to this equation here. So according to that calculations, the nanoporous films have about 20% porosity, while the templated highly porous films have about 35% porosity. Nevertheless, these numbers are likely to be underestimated because during the loading, of the tip into the surface, there is some pore compaction happening. Actually, we can see it from this indentation imprint here in this image. Also, we can observe it from the shape of the low displacement curves, especially for the highly porous samples. There is this flattening of the curve at the low loads that, yes, actually can be attributed to the pore collapse. Okay, in terms of magnetic properties, so we focused our attention to these three fields that have the same gallium content in the composition, but they have different porosity levels, so fully dense, nanoporous, and microporous or highly porous iron gallium film. So we can observe that all of these films have soft magnetic behavior with very low coercivity, and they also have in-plane easy access. So it is easier to magnetize these films in plane, applying magnetic field in plane rather than out of plane. The porosity causes some changes in magnetic behavior when measuring out of plane, but in fact, I will not go into a lot of details trying to explain that and focus more on the in-plane changes caused in plane. So for us, what is important to see is the saturation field. If the porosity changes the saturation field of the films, because this is where the maximum magnetostriction can be obtained. Because this field, all the domains are oriented with the magnetic field. And we can indeed observe that the nanoporosity decreases the saturation field slightly as compared to the fully dense replica sample. So that, in other words, means that we can induce the maximum magnetostriction in this field, applying smaller magnetic fields. And well, we also tried to demonstrate the proof of principle, magnetoelectric actuation, that we can indeed induce some strain in these nanoporous iron gallium films, and that this strain can be transferred to the second phase material. So to do that, we coated our electrodeposited nanoporous iron gallium fields with the polymer PDF-TRFE. This is a polymer that has some piezoelectric properties, so it can induce some charges on its surface when it is strained. So yes, this is the topography image of the polymer that was obtained using the piezophore spectroscopy. So we can see that this shape actually repeats the grain structure of the iron gallium, and we can see these kind of spaces between the grains. So these are the results that we obtained using this method. So the red loop, butterfly loop here, is a characteristic behavior for the polymer when there is no magnetic field is applied. But then when the magnetic field is turned on, we can observe that the amplitude and the coercive voltage of this polymeric material is actually changed. So this is a direct evidence of the magnetoelectric coupling between these two materials. And I have to say that it was not possible to induce any changes in electric polarization of this polymer using the fully dense replica. So when we used, instead of nanoporous electrodeposited iron gallium films sputtered layers, there was absolutely no change in the shape of this one. So this again confirms that there is some magnetostriction in these iron gallium films, and we believe that this is due to the presence of nanopores. So in fact, now we are trying to fill the large pores of iron gallium films with this polymer, but there are some tricks as always, but this is to be studied further. So to summarize my talk, iron gallium alloys with variable gallium contents were grown onto rich silicon substrates, and we could induce different porosity levels in the films. The mechanical properties of the electrodeposited films were assessed depending on as a function of the porosity level and also the gallium content in the films. So we found that both the hardness and elastic modulus decrease when the porosity is increased. However, the plasticity index is higher for these films. Then we could also demonstrate the magnetoelectric proof of principle using these nanoporous electrodeposited iron gallium films. And as a general conclusion for this work, the obtained results can be appealing for the fabrication of various biocompatible sensor electrodes. And with this, I finish my talk, and I thank you for your kind attention. Thank you.
Thank you. Thank you, Aliona, for nice talk. We have time for 1 or 2 short questions.
Yes.
Do you have any questions? Oh, Elizabeth.
Yeah. I have a quick question. Very nice talk, Aliona. I'm just wondering, is there a target concentration of gallium and iron that's important for the magnetostriction?
Yes, yes. So, well, let me share the presentation again. So it's actually here. So from this graph, we expect to have maximum magnetostriction at around 20% of gallium. And the second magnetostriction peak here is around 30% of gallium. So, but if we check the literature, most of the works are dealing with the iron 80, gallium 20%. Yes.
And would that be influenced by the porosity or this and the structure?
I think so. Yes, definitely. There is not so much research done on the magnetostriction in nanoporous fields, because in fact it's quite difficult to study it, because most of the methods rely on bending the substrate, and here we just can't, because actually the film is grown on the rich silicon. But definitely the structure, the microstructure, phase composition, the thickness will influence the magnetostriction behavior. Yes. Definitely. And in fact, even in this graph, I think, so Q stands for quenched iron gallium films, and SQ is slow cooled. And even so they have similar composition, but they were prepared using different methods, and we see that the magnetostriction coefficient is slightly different for these materials. So there is plenty of parameters that can influence the resulting properties. Mm-hmm. Yes.
Thank you. Please.
So you mentioned about to fill some materials. Yeah?
Some materials. Yeah. Mm-hmm. Yes.
What are the prospects? To fill with which materials? And what do you expect?
You mean which materials we can use to fill the pores?
Yeah.
Yes, that's an interesting question. I think the answer would depend, well, let's say the material selection would depend on the properties of the composite that we want to investigate and the application of this composite. So, for example, now we are trying to fill the pores. You see my screen right now? Yes? Okay. Yes. So we try to fill these large pores of iron gallium with the same kind of polymer, so with a PVDF-TRFE. So we try to do that by spin coating, but then we are not sure that we can actually penetrate through the whole through the whole depth from the material. So we try to do electrophoretic deposition, but still it's challenging because we don't know how to make sure that the pores are filled completely with this polymer. Yes, and we do that trying to maximize the changes in the electric polarization that we can induce in the film, so that we can generate more electricity using external magnetic field. And like the final goal of this study is to stimulate the cells. So then we have these porous iron gallium films filled with the ferroelectric polymer, and then we can put the cells on top and stimulate them using magnetic field. But still, we are quite far from that. We are now just trying to prepare good quality composite material where we have good interface between the iron gallium, between the magnetostrictive part and the piezoelectric part. Yes, but in general, this can be something else. For example, we can immerse this iron gallium film in a liquid, in a dielectric liquid, and we can try to modulate the properties of the magnetic properties of iron gallium by applying voltage. This is for converse magnetoelectric effect, and in our group we are also doing that. So that could be also interesting. For example, trying to reduce the coercivity in these films for some magnetic applications. Yes, these are the two applications that I see easily, let's say, but there must be some others.
Thank you.